This video is a review of slope fields and differential equations. The following problems will be considered calculator active, so we will use our graphing calculator as needed. Number 1. Which of the following shows the slope field for dy dx equals y over 2 minus x? We are like detectives looking for clues. Start by focusing on the fact that we have this lonely y in the numerator. That means when y is equal to 0, dy dx will equal 0, except when x is equal to 2. When x is equal to 2, the denominator will also equal 0. That would give us 0 over 0, which is an indeterminate case, and there should be no slope there. So maybe that's where we should start. There should be no slope at the point 2, 0. So in A, we see no slope at 2, 0, so far so good. In B, they are saying that the slope is 0. That's no good. There should be no slope there. Again, for C, at 2, 0, I see slope of 0. That's no good. There should be no slope there. Okay, this one's okay, and E again has a slope of 0 at 2, 0. So we have narrowed it down to either A or D. Both of these have slopes of 0 everywhere else that y is equal to 0. So time to move on to the next clue. Let's keep focusing on the denominator. When x is equal to 2, the denominator will be 0. So dy dx will be undefined when x is equal to 2. That means we should have a vertical asymptote at x equals 2. Well, both of these have a vertical asymptote at x equals 2. So next clue. Let's think about when dy dx will be positive. When the numerator is positive and the denominator is positive, the fraction will be positive. In other words, when y is greater than 0 and when x is less than 2. When x is less than 2, the denominator will be positive. So, where these two conditions hold, we should see nothing but positive slopes. Here I've highlighted the sections where y is greater than 0 and x is less than 2. Only D has the positive slopes, so the answer is D. In retrospect, this clue alone would have told us that the answer is D, because D is the only slope field that has all positive slopes in the region where y is greater than 0 and x is less than 2. Number 2. The slope field for a certain differential equation is given. Which of the following could be the differential equation that defines the slope field? As I study the slope field looking for interesting characteristics, I notice that we have a slope of 0 all along the line y equals x. In other words, dy dx will equal 0 whenever y equals x. So, which of these equations will give us dy dx equals 0 whenever y is equal to x? When y and x are the same value, y minus x will equal 0. So option A works. Option C similarly will give us 0 whenever x and y are the same, like 3 minus 3 will be 0. So option C works. Option B will not necessarily give us 0 when x and y are the same. For example, if x and y are both 2, x plus y is 4. So option B cannot be the answer. Similarly, we can eliminate option D, because if x and y were both 2, then that would be 4, not 0. Study the remaining two options and ask yourself, when will dy dx be positive? For option A, dy dx will be positive when y is greater than x. In other words, we should have positive slopes above the line y equals x. And I see negative slopes, so that means that option A is out. Now look at option C. dy dx should be positive when y is less than x. In other words, I should see positive slopes everywhere below the line y equals x. And that's exactly what I see. So the answer is C. For the next two problems, we will find the general solution of the differential equation. This means we will get rid of the derivative and turn each of these into regular y. We do not necessarily have to get y by itself at the end. Let's start by rewriting y prime as dy dx. This is a separable differential equation. So the game is, let's get all of the y's on the left and all of the x's on the right. I notice that most of the x's are already on the right-hand side. We just need to get dx over here to the right. And we can easily do that by multiplying both sides by dx. Now all of the x's are on the right. We just need to get all of the y's on the left. So let's get the factor y squared plus 4 over to the left by dividing both sides by y squared plus 4. So now we have this. Since all of the y's are on the left and all of the x's are on the right, we can integrate both sides of the equation. On the left side, we will use this memorized rule. This is a perfect match for arctangent when a is equal to 2. A will always be the square root of this constant. So on the left side, we will now have 1/2 arctangent y over 2. The right-hand side looks very similar, except when the degree of the denominator is exactly 1 more than the numerator, we are going to use u substitution. And in this case, we will let u equal x squared plus 4, which means that u prime is 2x. Making the substitution, we now have u in the denominator. Instead of dx, we write du over u prime, which is 2x. And we notice that the 2x in the numerator will cancel out the 2x in the denominator. On the right-hand side, we now have the integral of 1 over u du. But this is another memorized rule. The integral is natural log of the absolute value of u plus c. So now we have this. Substituting x squared plus 4 back in for u, and we have the solution to the differential equation. Notice that we no longer need the absolute value symbols because x squared plus 4 is always positive. For number 4, we have another separable differential equation. So we would like to get all of the y's on the left and all of the x's on the right. Let's start by getting dx over to the right-hand side by multiplying both sides by dx. So all of the x's are now on the right. We just need to get this y over to the left. We can do that by dividing both sides by y. Now we have this. Since all of the y's are on the left and all of the x's are on the right, we can integrate both sides of the equation. On the left side, this is a memorized rule. We know that the integral of 1 over y dy is the natural log of the absolute value of y plus c. I said absolute value and then I didn't put absolute value. That's because in the directions they mention that x and y are both positive, so we don't actually need the absolute value symbols. On the right-hand side, I think I will pull the 4 outside of the integral as a 1/4 before I do anything else. Also, let's rewrite the square root of x as x to the negative 1/2 power. Power rule of integration. Adding 1 to this exponent gives us x to the 1/2 power. Dividing by 1/2 is the same as multiplying by 2. 1/4 times 2 is 1/2. So this is the general solution to the differential equation. For the next two problems, we will find the particular solution of the differential equation that satisfies some initial conditions. This time we will write our answer in the form y equals f of x. For number 5, this is a separable differential equation. So let's get all of the y's on the left and the x's on the right. To begin, let's move the dx over to the right-hand side by multiplying both sides by dx. Now we have this. Let's get this y factor over on the left by dividing both sides by cosine squared y. Now that we have all the y's on the left and the x's on the right, we can integrate both sides of the equation. The left side will match a memorized rule if I remember that 1 over cosine squared y is the same as secant squared y. The derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. Similarly, the antiderivative of sine x is negative cosine x plus c. We are looking for the particular solution that satisfies this initial condition. So let's use this fact to find c. When x is 0, y is negative pi over 4. So here I've put 0 in for x and negative pi over 4 in for y. But the tangent of negative pi over 4 is negative 1. And the cosine of 0 is 1. So therefore we have negative 1 plus c on the right-hand side. Adding 1 to both sides, we get c is equal to 0. Putting 0 in for c, we have tangent y equals negative cosine x. We can sort of get rid of the tangent by taking the arctangent of both sides of the equation. So this is the particular solution to the differential equation that satisfies the initial condition. Number 6. Y changes at a rate that varies jointly with x and the reciprocal of y. Y at 0 equals negative 3 and y at 1 equals negative 4. Quick side lesson. Y varies jointly with w and x means y equals k times wx. When they say y changes at a rate, that means dy dx. When they say it varies jointly with x and the reciprocal of y, that means it equals k times x times 1 over y. This is a separable differential equation. So let's get all of the y's on the left and all of the x's on the right. Let's start by moving the dx over here by multiplying both sides by dx. So far we have this. Now let's get this y over here by multiplying both sides by y. Now that we have the y's on the left and the x's on the right, we can integrate both sides of the equation. The antiderivative of y is 1/2 y squared. Similarly, on the right-hand side, we have 1/2 kx squared, and here I will put the plus c. Let's use the first initial condition to find the value of c. When x is equal to 0, y is equal to negative 3. Substituting 0 for x and negative 3 for y, we have this. However, this entire term has a value of 0. So that gives us c is equal to all of this, which is 9 divided by 2. Substituting c back into the equation, we have this. Let's use the other initial condition to find the value of k. When x equals 1, y equals negative 4. So substituting 1 for x and negative 4 for y, we have this. Squaring the negative 4 and the 1, we have this. Multiplying both sides of the equation by 2, we have this. Subtracting 9 from both sides, we have k is equal to 7. Let's put 7 in for k right here. So now we have this. multiplying both sides of the equation by 2 gives us this. We can get y by itself by taking the square root of both sides. I will temporarily put y equals plus or minus the square root of 7x squared plus 9, but only one of these is actually the solution. It will either be plus or minus. Let's use the initial conditions to decide. This first initial condition makes it obvious. When x is equal to 0, y should equal negative 3. So if we let x equal 0, we will have the square root of 9, which would by itself be positive 3. The only way we're going to get negative 3 for the answer is if we put a negative in front of it. The solution that satisfies the initial conditions is y equals negative square root of 7x squared plus 9. Here is the setup for number 7 through 10. A bowl of soup, initially 140 degrees, is placed in a cool room that has a constant temperature of 68 degrees. The soup's temperature, y, changes at a rate that fits the differential equation dy dt equals negative 0.2 times y minus 68. Y is measured in degrees, and t is measured in minutes. Number 7. Find the second derivative in terms of y and t. You do not need to simplify your answer. To find the second derivative, we will take the derivative of the first derivative. When I see a constant in the front, I'm just going to bring that down. And then I will move on and take the derivative of whatever is left. Taking the derivative term by term, the derivative of y is dy dt. But the derivative of a constant is 0, so I write nothing. However, we must write the second derivative in terms of y and t, not dy dt. So we can substitute the equivalent expression for dy dt, negative 0.2 times y minus 68. We can put this expression in right here. So negative 0.2 times y minus 68. The direction said we don't need to simplify, so that's it for number 7. Number 8. Use a tangent line approximation with initial condition 0, 140 degrees to approximate the soup's temperature after 2 minutes. Whenever they ask us to find the equation of a tangent line, we love to use point-slope form because all we need is a point and the slope. And here they have given us a point, the initial condition 0, 140 degrees. All we need is the slope. Since the variables in this case are y and t, I will use t instead of x in my equation. In order to find the slope, all we have to do is evaluate the derivative at the point 0, 140. Since the first derivative is written in terms of y, all we have to do is plug in 140. This turns out to be negative 14.4. Now that we have a point and the slope, we can write the equation of the tangent line. It goes y minus y is equal to the slope times t minus t. Well, t is just 0, which we don't really need to write. Adding 140 to both sides, we have y is equal to negative 14.4t plus 140. We can use the equation of the tangent line to approximate the temperature at time t equals 2. Evaluating at t equals 2 gives us this. The temperature after 2 minutes is about 111.2 degrees. Number 9. Is the tangent line approximation in number 8 an overestimate or an underestimate of the true temperature after 2 minutes? Justify your answer. A tangent line approximation will give you an underestimate when the curve is concave up, because the tangent line is always below the curve. It will give you an overestimate when the curve is concave down, because in that case the tangent line is always above the curve. In problem number 7, we came up with this equation for the second derivative. We can evaluate the second derivative at the point 0, 140 to find out if the curve is concave up or concave down near this point. We get positive 2.88. The second derivative is positive at 0, 140, so the temperature graph is concave up near 0, 140. Thus, the tangent line approximation is an underestimate. Number 10. Find a function y of t that gives the soup's temperature after t minutes by solving the differential equation using the initial condition 0, 140 degrees, and use it to find the soup's temperature after 2 minutes. Show all work and write your final answer in the boxes below. This is a separable differential equation. Let's get all of the y's on the left and the t's on the right. To begin, let's get dt over on the right by multiplying both sides by dt. So far we have this. Let's get y minus 68 over to the left-hand side by dividing both sides by y minus 68. Now that we have all the y's on the left and the t's on the right, we can integrate both sides of the equation. This is going to be a mental u substitution. However, I'm going to show it for instructional purposes, and then I'll go back and do it again mentally. We would let u equal y minus 68. In that case, u prime would be 1, which is our clue that we should be able to do this mentally, anytime u prime is a constant. So if we rewrite, we would get the integral of 1 over u, and instead of dy, we would write du over u prime. But u prime is a 1, which we wouldn't even need to write, so we would have this. Then the antiderivative of 1 over u is natural log of the absolute value of u plus c. So on the left side of the equation, we would end up with the natural log of the absolute value of y minus 68. And we won't put the plus c because we will save that for the other side of the equation. These 3 lines right here, we did not need to show. We could have done this mentally. We could just look at this and say, u is y minus 68. So u prime is 1. When you do u substitution, you divide by u prime. But dividing by 1 changes nothing. So we move on with the antiderivative. The antiderivative of 1 over u is natural log of the absolute value of u plus c, which we will save for the other side. So we can go straight to this without actually showing the u substitution. Meanwhile, on the right-hand side, the antiderivative of negative 0.2 is negative 0.2t. And there's your plus c. Speaking of plus c, let's use this initial condition to find the value of c. Substituting 0 for t and 140 for y, we have this. That means c is equal to the natural log of 72. Putting natural log 72 in for c, we have this. I am dropping the absolute value because y minus 68 will be positive as long as y is above 68 degrees. And 68 degrees is room temperature, so the soup will not fall below 68 degrees. To solve this equation for y, we can exponentiate both sides of the equation, meaning we can drop a base e on both sides, making the left and the right an exponent of e. Base e and natural log are inverse functions which cancel each other out. So on the left side, we just have y minus 68. On the right side, I'm going to use this property of exponents that e to the a plus b can be rewritten as e to the a times e to the b. So that will give me e to the negative 0.2t times e to the natural log 72. But base e and natural log are inverse functions, which cancel each other out. So this will just leave 72. So now I have this. Adding 68 to both sides, we get y at t is equal to 72 e to the negative 0.2t power plus 68. We can evaluate this equation at time t equals 2 to find the temperature of the soup after 2 minutes. This turns out to be 116.263 degrees. Kabam! For number 11, we just need to find this antiderivative. Let's try u substitution. U will equal x plus 3, which means that u prime will equal 1, which really won't do anything. Let's see what happens when we do the substitution. We get the integral of 2x times the square root of u. Instead of dx, we will write du over u prime, but u prime is 1, so we write nothing, so that's what we have. At first, we are nervous because the x's did not cancel out. But maybe we can do a secondary substitution. Staring at the tiny equation u is equal to x plus 3. If we were to solve this equation for x, we would subtract 3 from both sides, which would give us x is equal to u minus 3. If we use this to substitute back in for x, we end up with the integral of 2 times u minus 3 times, well, instead of the square root of u, I will write u to the 1/2 power, du. Let's pull the 2 out in front of the integral, so we have this. Now let's distribute u to the 1/2 power. So now we have this. We got the 3/2 by adding 1 plus 1/2. Now we integrate term by term. Adding 1 to 3/2, we get 5/2. Then we divide by the new exponent. Dividing by 5 over 2 is the same as multiplying by 2/5. Bring down the negative 3. Adding 1 to 1/2 is 3 over 2. Dividing by 3 over 2 is the same as multiplying by 2/3. And we notice that these 3's will cancel each other out. Distributing the 2 gives us this, and substituting x plus 3 back in for u gives us this. Number 12, consider the differential equation dy dx equals e to the x plus y minus 1. Show that the second derivative is equal to e to the x plus y squared. The second derivative is the derivative of the first derivative. So we just need to take the derivative of this expression term by term. The derivative of e to the something is e to the something. However, we have to employ the chain rule and multiply by the derivative of this inner function. So taking the derivative of x plus y term by term, the derivative of x is 1, and the derivative of y is dy dx. Let's do a substitution here so we can replace dy dx with what it is equivalent to. So we're going to put this right here. But then we notice that we have like terms here and here. 1 minus 1 cancels itself out. So now we have this. And oh look, e to the x plus y times e to the x plus y is e to the x plus y squared. And we have now shown that the second derivative is indeed equal to e to the x plus y squared. The question is, do I have to show all of these steps, really? Yes, you do. We knew what the answer was right from the beginning. The whole point is to show exactly, step by step, how to get there.